So for this simplest possible example, we've got second derivative of y equals 5. And we can get rid of one of those derivatives by just integrating. Let's say we integrate with respect to t. So we get one of the derivatives cancels out with the integral. So we get y prime equals 5t plus a constant. And then how do we deal with that other derivative?
Then we take another integral on both sides.
Integrate one more time. That cancels out the other derivative. So we get just y equals, and what's the integral of 5t?
5 t squared.
And then the integral of this c here?
Plus ct, and then plus c again.
Yeah, and since we're gonna need another constant, a second constant, let me label this C1, and then the other constant we'll call C2. And we can't just combine these constants because one of them has a times t and the other one doesn't. They're not like terms, so we can't combine them. But this would be our general solution. This essentially describes the set of all functions whose second derivative is 5. And note that there's essentially two degrees of freedom here. There's two unknown parameters that could be any real numbers. So instead of just having one variable where we can plug in anything we want, we have two variables where we can plug in anything we want. And that means in order to solve that, how do we usually find the C value in a first order equation?
You would be given like an initial condition.
Yeah, the initial condition. So let's say we have the initial condition. Let's say we know that, let's say y of 0 equals 5. Well, we already use 5. Let's say y of 0 equals 10.
Vitamins and
minerals. So if we actually plug these in, plug in 0 for y, sorry, plug in 10 for y, plug in 0 for t, and what does that tell us?
Then C2 would equal 10.
Yeah. But note that that's not enough information because we still don't know C1. So we're going to need one more piece of information for the initial conditions. And there are several ways that other piece of information can be given. In some situations, you have, instead of having 1 point on the graph, you're given 2 points on the graph. And that's typically called a boundary value problem. Boundary in the sense that, like, let's say you've got some time interval. You know, at the beginning, it's some value. At the end, it's some other value. Those are basically the boundaries of that interval. The problem is boundary value problems are not generally always going to be solvable. There's not really a good existence and uniqueness theorem for boundary value problems. If you know 2 points on the curve, that doesn't always narrow it down.
Thank you.
Like, for instance, if you have 2 points, there may be multiple parabolas or whatever going through those 2 points. So boundary values don't always narrow it down to one solution. But I think in this case they do. But in general, that's not guaranteed. But instead, the initial conditions are usually the value of the function at that 1 point, and also the slope of the function at that 1 point. The initial conditions will be something like, at time 0, the value is 10, and the first derivative is, let's say, -2. So this is typically what an initial value problem will look like for second order. You'll be given a second order differential equation, the value of the function at some time, usually time 0, but it doesn't have to be, and the first derivative of the function at a time, usually at the same time, but it doesn't have to be. So then what you can do is plug this in as well. And of course, to do that, you'll need to take the derivative of your general solution. So let's try that also. Derivative is going to be, actually, we could just backtrack to this one in this case. But generally, you would just take the derivative of whatever your general solution is. Derivative of 5t squared over 2 is just 5t. Derivative of C1t is C1, derivative of C2 is 0. Then plug in this information, 0 for t, and -2 for y prime. And then you can solve for C1. In this case, that just turns into C1 equals -2. But that's going to be varying levels of complexity depending on exactly what your general solution is. In many cases, plugging in 0 for t won't just get this term to cancel out entirely, depending on what the function is. But even if you don't get a term to cancel out entirely, each part of the initial condition gives you an equation with C1 and C2. Once you've got two equations with C1 and C2, you can treat that as a system of equations and solve for C1 and C2. Then you can plug those back in to the general solution, and that would be your specific solution. It's a solution to the original differential equation that matches these restrictions. It has this value at time 0 and has this slope at time 0. Any questions on that so far?
Just to go off for the boundary, you said boundary value, was it boundary condition or boundary?
Boundary values, yeah.
Boundary value, okay. So for the,
you can say boundary conditions also.
okay. So for the boundary value problems, if we're given another point, would we have to use like point slope and try to find the slope at that point? And then
no, because the thing is those 2 points, the curve between those 2 points is not going to be a straight line. If you take this rise over 1, that gives you the slope of the secant line. Like for instance, if you have this point and this point, rise over 1 would tell you the slope of the secant line, but that's not necessarily going to be the slope of the tangent line at either of those points.
okay.
The mean value, or the mean value, intermediate value, one of those theorems tells you that we can guarantee there's some point on the curve where the tangent line matches the slope of the secant line, but it doesn't tell us where that point is. So that's not really very useful.
Oh, okay.
What you could do with the boundary value problem, if you have, for instance, this point that the curve must go through and this point that the curve must go through, you could just plug in these t and y values into your general equation and separately plug in these t and y values to your general equation. That would still get you two equations with C1 and C2. But I don't think there's a general rule saying that those that has to be solvable. It might be the case that you get infinitely many solutions, or it might even be the case that you get no solutions. For example, it might be the case that you have a point and then another point that's higher up, but the same t value. That wouldn't even be a function. So not every pair of boundary values leads to actually having a specific solution.
Okay.
Or maybe you've got, for instance, an always increasing function, but both of the boundary values are the same value, or same y value, but different t values. That might not be possible. But we can set up an existence and uniqueness theorem for initial value problems, where you've got the value and slope at some t value. And I think it's very useful to look at this in terms of the physics applications of this, because if we're talking about, like, let's say y represents position. If we're talking about a function that represents position, if y represents position, then what would y prime represent? If that's derivative of y with respect to time, what would we call that?
It would be speed.
Yeah, that's the speed. And then if you take the second derivative, what would that be?
That would be acceleration.
Yeah. So that means if your function represents position as a function of time, the differential equation is just describing how acceleration, speed, and position are related to each other, usually something involving forces, because the net force on an object equals mass times acceleration. So if you can write out some expression describing the total of all the forces acting on an object, especially if the forces depend on position and speed, then you can say that total force equals mass times the second derivative, And that often leads to second order differential equations. And then the initial conditions would just be knowing where the object is at time 0 and how fast the object is moving at time 0. So if you know something about the forces and you know where the object is and how fast it's moving at some time, that can be turned into an initial value problem. So this idea of second order equations has tremendous application in physics for exactly that reason.
Okay.
Any questions on that so far? So let's try some other examples then. The main idea I wanted to get at is that because the second derivative kind of implies integrating twice, you're going to get two constants of integration, C1 and C2. So you need two facts about the initial situation to find C1 and C2. But let's take a look at a more generalized case. We're not going to be looking at every second order equation here, but if we restrict our search to just linear differential equations, some very useful patterns emerge. If it's linear, and of course, second order means we're going to have a y double prime, we're going to have a y prime, we're going to have a y. And if we're specifically requiring it to be linear, how do those have to be combined with each other? What's the only stuff we're allowed to do if this is going to be linear?
Would you only be allowed to have, function t?
Yes, exactly. We can multiply each one by a function of t. This is basically like the idea of linear combinations from 22a. In fact, we are just creating linear combinations of these three terms. We can multiply each one by a scalar, and in this context, scalar means either a constant or a function of t. So let's say a of t, b of t, and c of t. We're allowed to add those together, and the result could also equal some other function of t. So a linear second order differential equation is one of this format. And have you seen the term homogeneous yet?
I think, you mentioned it in lecture, yes.
So how are we defining that in this context?
What do you mean, G of t? Yeah, G of t.
Yeah. Homogeneous means there is no G of t. G of t is 0. And that doesn't mean the equation has to be written as like a bunch of stuff equals 0. G of t doesn't have to be on the other side of the equation. G of t is specifically the term that doesn't have any y or y prime or y double prime in it. So when you're asking, is this equation homogeneous, what you should be really looking for is there a term without y in it or not? For example, if we wrote y double prime equals 3y, that doesn't really look like this format. You wouldn't say, oh, it's equal to 0. But this still counts as homogeneous because it does not have a term without y in it. That term without y in it is usually called the non-homogeneity because it's what makes the equation non-homogeneous. Or it's also called the forcing function. Because in applications in physics and engineering, the extra non-homogeneity here usually represents some sort of external force being applied to the system. Or in electrical circuits, for instance, this non-homogeneity usually represents an external voltage, maybe from a battery or a generator or something, applying extra voltage to the system. But it typically is some sort of extra push coming in from outside the system. And that itself might be 0 or might be a constant or might be some function of time. And of course, it's a lot easier to solve homogeneous equations versus non-homogeneous equations. So we're going to start with homogeneous equations. We'll start with a of t times y double prime plus b of t times y prime plus c of t y equals 0. A homogeneous second order linear differential equation. And also, what do you think would be the easiest types of functions to use for a, b, and c?
Would it be just constants?
Yeah, so we're going to start with just constants. So that becomes just a constant a times y double prime plus a constant b times y prime plus a constant c times y equals 0. So this is the case we're going to be most looking at throughout probably the first half of chapter 3. And then we're going to add in non-homogeneities, forcing functions, and see what happens. But it turns out that to solve a non-homogeneous linear differential equation, usually what you do is you start by pretending it's homogeneous, just pretend the g of t isn't there, solve that to find the homogeneous general solution, and then figure out what extra needs to be attached to that to make it work for g of t instead. But solving the second order linear homogeneous differential equation with constant coefficients is really the heart of all of chapter 3. And I think in a lot of ways, really the heart of 22B in general. This is the, if I had to pick one part of 22B to call the core idea of the whole course, I think this would be it. Solving second order linear differential equations with constant coefficients. Starting with the homogeneous case, and then building up to how to deal with non-homogeneities as well. And as before, since this involves a second derivative, the process of solving it isn't going to directly involve taking integrals, but it's equivalent to finding an integral twice, which means we're going to end up with 2 unknown constants. So we will need 2 pieces of information as the initial conditions. Any questions on that so far? Then let's take a look at what you might call the simplest homogeneous case. Because the one we were looking at before, y double prime equals 5, that's non-homogeneous. The 5 would be the g of t there. Let's take a look at a homogeneous case. Let's say we just have 1 y double prime plus, let's say 0 y prime plus negative 1y. Y double prime minus y equals 0. I think this is about as simple as we can make this format and still be in this format in an interesting, useful way. Because then we just get y double prime equals y. And think back to what you know about functions. Do you know of any functions where the second derivative of a function equals the function itself? What's a function that doesn't change when you take the derivative twice?
I think it's either cosine? I think it's either cosine or sine or the e to the x or e to the t.
Well, let's try those. If we were dealing with a sine or a cosine, let's say y equals sine of t. What's the first derivative of sine of t?
Cos t.
Yeah, cosine of t. And then the second derivative?
Oh, minus sine t. Okay.
Yeah, you get a negative when you take the second derivative. So that would be the solution to y double prime plus y equals 0, because then y double prime would have to be the opposite of y. Mm-hmm. And same thing for cosine. Cosine, when you take 2 derivatives, ends up being negative itself. So sine and cosine are certainly possible solutions to other second order equations, but they're not solutions to this one. But yeah, let's try e to the t and e to the negative t. If we try y equals e to the t, then the first derivative is e to the t, the second derivative, all the derivatives are just going to be still e to the t. So since the function and the second derivative are the same, that makes this differential equation true. But let's try the e to the negative t as well. If y is e to the negative t, what's the first derivative?
Negative e to the negative t?
Yeah, which is different. But then when we take the derivative again, what happens?
And then it becomes e to the negative t.
Yeah, the extra negative from the chain rule cancels out the negative that was already there. So this also works. E to the negative t is a solution. E to the t is also a solution. So we get 2 solutions. We're usually going to call these y1 and y2. And we now have a set of 2 different solutions. And we're usually going to call this a fundamental set of solutions. The actual general solution to this differential equation, though, since we have 2 solutions, we've got e to the t, and we've got e to the negative t. How do you think we could modify those or combine them to get more solutions? Because we should expect infinitely many.
Would it be to have constants in front of them, like multiply them by a constant?
Yeah, we could multiply each one of these by a constant. And the reason that works, if you had a times a constant here, let's say C1 times e to the t, the derivative would just still be C1 e to the t, the second derivative is still C1 e to the t. So we still have the fact that y double prime equals y. In fact, even here, if you had C2 here, you get negative C2 e to the negative t, and then positive C2 e to the negative t. So we still get the fact that y double prime equals y. And yeah, we can also add them. Because if you add them together, the whole idea of derivatives distributes across addition. If you take the second derivative of y1 plus y2, the second derivative distributes. You get y1 double prime plus y2 double prime. And then we're subtracting y1 plus y2. We already know that y1 is going to cancel out y1 double prime, and y2 would cancel out y2 double prime. So you still end up with 0. So in general, if you have two different solutions, or any number of solutions really, if you have any number of individual solutions to a differential equation, as long as it is linear and homogeneous, those have to be true, then linear combinations of your solutions can be used to build more solutions. And this turns out in this case to be our general solution. Because like I mentioned earlier, we should expect a second order differential equation to involve two unknown constants, because it sort of implicitly involves two integrals. So we should expect to end up with two unknown constants, and these are what they are. And note that we can't combine these into one constant because e to the t and e to the negative t are fundamentally different kinds of functions. We would say in this case that they are linearly independent functions, and we can look into what that means in a little more detail later. But this is the general format for the general solution of a second order homogeneous differential equation. As long as it's linear and homogeneous, technically the coefficients don't even have to be constants. In general, if you have a second order linear homogeneous differential equation and you have any two solutions, you can build more solutions just by taking linear combinations of those. So this is going to be the typical format for the general solution of a second order differential equation, as long as it's linear and homogeneous. Any questions on that so far? So let's take a look at the existence and uniqueness idea in order to guarantee that we can get a solution. Let's say we have initial conditions. Let's say y of 0 equals y naught, and let's say y prime of 0 equals v naught. Since y prime just represents velocity anyway, assuming y is position. So let's say we have values of initial position and initial derivative, initial slope. And we want to find values of C1 and C2. What you can do then is plug in 0 for t in this whole thing. So you get C1 times y1 of 0 plus C2 times y2 of 0 equals y naught. And then also you want to take the derivative. But derivative distributes across addition, so you just get C1 y1 prime of 0 plus C2 y2 prime of 0 equals the initial velocity. That's now a system of two equations, two unknowns, so we should be able to use ideas from linear algebra to solve for C1 and C2. Any questions on that so far?
So then, if we were to solve this given system, we would have to, well, okay, we would have to have like values and then figure out what's the respective C1 and C2s, and then
yeah, because y1 and y2 are just going to be whatever functions you got from the original differential equation, the individual solutions.
Mm-hmm.
So y1 and y2 are presumably known functions. You can plug in 0 for t or plug in whatever t value you've got. So y1 of 0 and y2 of 0 are just numbers. Mm-hmm. Likewise, you can take the derivative. So y1 prime of 0 and y2 prime of 0 are also just numbers. And y0 and v0 are the initial conditions that would also be given. So the only unknowns here would be C1 and C2. And then you can solve that using any technique you want from linear algebra. I think perhaps the most useful one to use here would be to set it up as a matrix equation. That we could write this as a block of coefficients times a vector of unknowns equals some other vector. And what are the unknowns we're trying to find here?
The constants?
Yeah, those constants, C1 and C2. The other side of the equation is just the initial conditions, y0 and v0. And what are the coefficients of these unknown constants, C1 and C2?
Well, there would be the y10, y20, and the y primes.
Yeah. The top row is the individual functions that we found here, in this case, e to the t, e to the negative t. The second row would be the derivatives of those. And of course, these are all evaluated at 0 or whatever the initial time is, but I'm not going to bother writing that in at the moment. But this matrix is super important because this matrix of coefficients is what determines, do we even have a solution? Because if you have some matrix equation, let's say A times C equals B, where C is unknown variables and A is a coefficient matrix, what is it about A that determines whether you even have a solution or not? What has to be true about A to guarantee that this system has one and only one solution?
Is it that there's inverse?
Yeah, it's got to be invertible. Because if A is invertible, you can just multiply both sides by A and get C equals A inverse times B. That's one and only one solution. You can, assuming you can find the inverse, A inverse multiplied by B gives you a solution, so that guarantees there is one. But also a matrix only has one inverse, if it has an inverse at all. So that guarantees this is the only solution. So in general, no matter, and note that this didn't depend on what y0 and v0 are. No matter what the initial conditions are, we can guarantee there's a unique solution for C1 and C2 as long as this matrix is invertible. And this matrix being invertible depends entirely on our choice of y1 and y2. In fact, what's usually the fastest way to determine if a matrix is invertible or not? Yeah, if we use the determinant, the idea of take the determinant, and what does the determinant tell you there? If the determinant is,
if determinant is 0, then it's non-invertible, if I remember.
Exactly. So if the determinant of this matrix happens to be 0, that means it is non-invertible, which means we can't guarantee there exists a unique solution. In order to guarantee existence and uniqueness here, we need to have this matrix be invertible, which means we need the determinant to be non-zero. So let's try writing that out. We need determinant of this matrix to be non-zero so that we can guarantee it's invertible, so that we can guarantee specific values for C1 and C2 even exist. And again, note that this is true no matter what the initial conditions are. As long as we have initial conditions at all, and as long as this matrix is invertible, that we can guarantee there is a solution and only one solution. So let's try writing out that determinant. What is the determinant of this matrix?
Yeah.
It would be y1 times y2 prime minus the y2 minus y1 prime?
Exactly. So as long as this calculation results in something that's not 0, specifically at the initial conditions, but it can be demonstrated, I think it's called Abel's theorem. Abel's theorem implies that this determinant is going to be either always 0 for all t values or never 0 for any t values. So it doesn't really have to be specifically at the initial conditions. You can just check this anywhere. It'll be either always 0 or never 0. And we call this the Wronskian. That's Wronski with a W. The Wronskian determinant, usually written as W of y1 and y2. So you can think of W as a function that takes two functions as input and gives you a number as output. If that number is 0, that means those two functions aren't really enough information. Specifically, we would say the functions are linearly dependent if the Wronskian is 0. If the Wronskian is 0, those two functions are linearly dependent. They're not really different functions at all. But as long as the Wronskian is anything other than 0, that means those two functions are linearly independent. They really do count as different functions. And having linearly independent functions guarantees that you do have enough information here to truly call this the general solution. Because as long as the Wronskian is non-zero, then no matter what the initial conditions are, you can guarantee solutions exist for C1 and C2. In particular, we can say only one solution exists. For a second order, it will always be a 2x2 matrix. If you're looking at a third order equation, you would expect 3 solutions, y1, y2, y3. So the Wronskian would be determinant of y1, y2, y3, y1 prime, y2 prime, y3 prime, and then a third row, y1 double prime, y2 double prime, y3 double prime. And for third order, you would need 3 sets of initial conditions. The function's value at time 0, the function's derivative at time 0, and the function's second derivative at time 0. So all this stuff still applies to third order, fourth order, any order you want. It just becomes more and more complicated, but it's still the same pattern. So Wronskian is going to be an n by n determinant, where n is the order of the differential equation you're talking about. Any other questions on that so far?
So we could use the Wronskian to figure out whether the equation, the y double prime itself, is like solvable, or?
It's really more about looking into your choice of y1 and y2. Are y1 and y2, formally we're checking are y1 and y2 linearly independent as functions.
Mm-hmm.
I generally think of that in terms of are y1 and y2 really different information, or is y2 just duplicating the information we already have in y1? And the purpose of all this is to check, are the solutions we chose, the y1 and y2, are those really enough information that we can find C1 and C2 for every set of initial conditions possible? Because if you don't have enough linearly independent functions, in particular, you need as many as the order of the equation. This is a second order equation, so that means we need 2 linearly independent functions, and linear combinations of those, of course, in order to be able to build a solution for any initial conditions they throw at us. If it was third order, we would need 3 linearly independent solutions in order to build all possible solutions. But for now, we're just looking at second order. But let's check this. Let's actually try writing out the Wronskian of e to the t and e to the negative t. So you could think of this as the determinant of a 2x2 matrix with the 2 functions in question on the top row, e to the t and e to the negative t. And then their derivatives. Derivative of e to the t would just be another copy of e to the t. Derivative of e to the negative t would be negative e to the negative t. And then when we write that out, as usual, we're just multiplying across the diagonals for the 2x2 determinant. E to the t times negative e to the negative t, what does that become?
Would that become 1 or negative 1?
Exactly, negative 1 because of the negative here. And the e to the t and e to the negative t cancel out. Minus the other diagonal. So what does the other diagonal multiply to?
And that would be 1.
Yeah. So the result of the Wronskian determinant is -1 minus 1, which is -2. So we say the Wronskian of these two functions is -2. That's not 0, which means these two functions really are linearly independent. And that tells us that linear combinations of them really do include all possible solutions. That no matter what the initial value is, we can find C1 and C2 uniquely for those initial values. So that's basically the existence and uniqueness theorem for second order linear homogeneous differential equations. Then in order to write out the general solution, you need two different functions, two linearly independent solutions. And to check linear independence, you would use the Wronskian determinant. As long as the Wronskian determinant of those two individual functions is non-zero, then that means those two functions really are two different functions, two linearly independent functions. And so you end up with being able to find C1 and C2, a specific solution for any initial values. Any questions on that so far?
Sorry, just to like clarify, for the when you're mentioning like the linear independence or linear dependence, are you talking about the two functions being not like relying on each other?
Yeah, very similar to the idea of linear independence for vectors. Like if you've got two vectors, we would say they're linearly independent as long as one of them isn't just a multiple of the other.
Okay.
There's no way you can write e to the -t as just e to the t times some scalar. They're genuinely different types of functions. But if you had had like e to the t and 5e to the t, those aren't really different types of functions. If you try writing out the Wronskian of e to the t and 5e to the t, you're going to end up with 0.
Okay.
And we can generalize this a little further also. Let's say instead of having this particular differential equation, let's generalize this to, let's say, a y double prime plus b y plus, or by prime plus cy equals 0. So now we're looking at any possible second order linear differential equation with constant coefficients and homogeneous as well. We still, even though a, b, and c are just some arbitrary constants, presumably we would know what those constants are in a specific problem. But no matter what a, b, and c are, we still have the idea that something times the function and something times its derivative and something times its second derivative have to add up to 0. That suggests that the function, its derivative, and its second derivative have to be the same type of function. And what type of function continues to be the same type of function when you take derivatives?
E to the t and e to the minus t.
Right. But not just e to the 1t and e to the -1t. It could be e to the anything t. Because if you take the derivatives of, like, let's say y is e to the rt, what would the first and second derivatives be?
Oh, it would be r e to the rt and then r squared e to the rt.
Yeah. Which means just a scalar multiple times the same type of function. So if we take this as our guess, if you just say, well, this looks like it should be an exponential function, so let's guess that y is e to the rt. Then we replace y with e to the rt. Y prime is going to be the same function multiplied by a constant, and y double prime is the same function multiplied by a different constant. So if we fill in our guess, so we've got a times r squared e to the rt plus b times r e to the rt plus c times e to the rt equals 0. This guess, I mean, we're basically taking a guess and plugging it in to see if it works. Is it possible for these to add up to 0? It looks like it should at least be possible because these are all e to the rt times something. They're the same type of function, so they should be able to combine. If we have the right constants, then they should be able to cancel out to 0. So it looks like this is at least possible. To verify what r is, we can just treat this as an equation to solve for r. And the reason this is going to work is that e to the rt now shows up in every term. So what can we do with that?
Oh, you can divide the whole equation by e to the rt.
Yeah, if we divide both sides by e to the rt, which is possible because e to the rt is never going to be 0, then we get AR squared plus BR plus C equals 0. And what kind of equation is that?
It would be a quadratic.
Exactly.
So factor.
Right. Factor it, or even if it's not factorable, you can use completing the square or quadratic formula to find values of R. And since this is a quadratic, we can expect up to 2 different values of R. So that means we're going to get y1 is e to the r1t, y2 is e to the r2t. So as long as your quadratic produces 2 different R values, these are your 2 solutions. You can run that through the Wronskian determinant, and you should find that as long as R1 and R2 are different values, the Wronskian is going to be non-zero. But this is generally how we solve second order linear differential equations with constant coefficients and homogeneous, of course. You assume that no matter what it is, you write it out in this format, ay double prime plus by prime plus cy equals 0, as long as a, b, and c are constants. Start with the guess that y equals an exponential function, e to the rt, or whatever coefficient you want to call it. Plug that and its derivatives into the differential equation, divide both sides by e to the rt, and it will become a quadratic. As long as you can solve that quadratic, that tells you the values for r. And as long as you get 2 different values, e to the r1t and e to the r2t are your 2 independent solutions. And then, of course, linear combinations of those with unknown coefficients c1 and c2 will give you the general solution. Any other questions on that?
Yeah, I think that definitely makes a lot more sense for the, and then just that, the whole portion with the, will be applied to how we can find like different unique solutions. We need to find the unique solution can be just defined by like the 2 initial conditions that we basically have.
Yeah, I would start by finding the general solution. So that it would look like C1 e to the R1t plus C2 e to the R2t. And then if you have initial conditions, you'd plug those into both the general solution and its derivative. And that gets you a system of 2 equations with C1 and C2 as the 2 unknowns.
Gotcha.
Solve for C1 and C2, and you've got your specific solution.
Okay, yeah. Got it.
Cool. All right, then feel free to email me if you have any other questions, and we can take a look at some more examples next time.
All right, thank you.
You're welcome.